Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. In this video today, we're going to take a look for the first time, we're going to delve deeper into x86 assembly language. So we're going to look at the statements we've talked about previously, like moves and adds and inks and decks and negates and things like that. So let's just jump right into it. So we were discussing in a previous lecture that there's, for every operation, there's a number of operands that we have to supply to it to do its job. Just, if I want to add two numbers together, I better find the two numbers that I add together, and so forth and so on. And then we also kind of briefly discussed the different types of operands that we can have. So again, this is just a refresher here. There are three different ways we can supply operands to an operation. And so just understand that not all of these work in all situations, so we just kind of have to get used to the rules for each of the operation, and because some of them are very specific with what the requirements are. So an immediate value, a hard-coded constant literal value, something that could be 8-bit, 16, or 32, so something like this, 11, 6, 5. And again, that integer expression idea, as long as the whole integer expression can reduce down to one very specific integer value, then it's perfectly allowed, as it's just when variables are involved that things are not okay anymore. And the one thing if you can think about things, there's a source and a destination to each of these operations, meaning everything goes right to left. So like even in any other language, you can't just say 5 equals x, right? You have to kind of say x equals 5, because everything kind of works its way. Well, it's mirror image for you guys, but everything kind of works its way right to left as you're working through a line of code. And so the same thing would apply here. I couldn't put like move 11 comma BL, because you can't take a literal value and jam something into it. It doesn't make any sense. So immediate values, pretty simple stuff. The registers, remember all the different registers. There's so many, there's 8 of them, plus all their little subparts, EAX and BL and CX and you name it, right? All these little, all the ones you see here. So I can use a register, and pretty much every register that I have, or say that when I'm running an operation, pretty much every operation has to use at least one register. There are different rules, and sometimes you can use variables and stuff like that. But for the most part, to do work on your computer, you have to move something out of RAM and onto the CPU and onto a register to make it work. So if you forgot the names of the other registers, you should probably go find that video or find that slide or find your notes on all those different registers, because we're going to be using those for the rest of the term now. And so memory, RAM. So again, remember, your entire program is running in RAM, and so is all of the variables, the global variables that you've set up, they're sitting in RAM. And so we can use that as long as we know the memory address, we can go there and do stuff with it, put information into it, get information out of it. And so, so again, use sensible names for your variables, count, value, total, that sort of thing. And you see that outside of immediate values, registers can go on either side of the comma for 2 operands and so forth and so on. And so the book, if you guys are my students rather than just people watching this from who knows where, so you understand that the book is trying to help you understand the different ways that you can set up the different operations. And these, so Reg 8, Reg 16, Reg 32, this specifically tells you the size of the register that's allowed. And so just Reg by itself could be any of them in any form. But then this is, I wish the mouse wouldn't go away. And then these are very much more specific. Signed register, or segment register, not signed register. You see S and you always think signed. Segment registers versus regular registers. And here are all the immediate values, 8-bit, 16, 32 general, and then memory. And then it's the same with memory, but generally speaking, if I can do memory, I can do registers. So it's very rare that you would see something that is just straight up memory and nothing else. So just to say, this is just to help you, because for a certain operation, you could have 5, 6, 10 different ways that you could shore up here and use the operands to get the job done. Okay, so let's take a look. Let me move my body over, and then we can kind of take a look at this. Oops, why am I'm gonna fix up my green screen stuff too. Okay, so in previous lectures, we've discussed how to set up variables, global variables, inside of our data segments of our programs. And so this is just to show you how things work when it comes to now using them on the other end inside of your code. So number byte 42. What is this? What would this be if this was C++? This would be character, and so this actually would be technically unsigned character, and then it would be unsigned character number equals 42. So that won't fit on one line here with everything I'm trying to show you guys, so I'll just cut this out. So just to understand, just to kind of bring yourself back and just see that this is how you would represent this, because this is unsigned by default. Byte becomes a character, so unsigned character number equals 42, semicolon, whatever, however you want to work it. So, okay, so there's that understanding. And now using this on this other end, there are two alternate ways you can go ahead and use it. And pretty much I've never seen anybody use it the alternate way, at least when it comes to normal variables. So if I want to move, which is a move operation, which we'll discuss in a couple slides, is just an equals operation. We've talked about it, but we've never 100% discussed it. I could say move number into AL. So this is take this variable and copy it onto the register, and they have to be the same size. This is one of those fun ones, like I can't be this because EAX is 32 bits, number is 8. So there's a mismatch there. And you can see, never look at this first thing that pops up, always find where the actual line of code that breaks. Operand or instruction operands must be the same size. That is the only error message you're ever going to get. There's nothing more verbose than that. And that just means there's a mismatch because number is 8 bits, EAX is 32. So I have to have a match. So AL is 8 bits, number is 8 bits. And now everything is good to go. And if I do a call dump regs, to see the result of that, and I'll do a call wait message just so I can make the program pause and show up on the screen, you go, oh my goodness, what am I staring at here? And then you're going to think you did something totally wrong. And actually, in the reality of this is you did everything exactly right. What is 42 in hex? But basically, 32 plus 10, so 2A. And you're like, and the AX register, and you look at this thing over here, AX, and you're like, oh my goodness, that's not correct. But the answer is actually in there, because the only thing we touched in this operation is the AL portion of the register, the load byte, the load 2 hex digits, and that's correct. Nothing else matters, because we're not using the rest of that EAX register, we're just using AL, so we actually did make this work out correctly. And if you really wanted to, just to prove that, we could move in right before this, we could move a 0 into the EAX register and do this again. And now you see everything kind of lines up because EAX turned to 0, then it got turned to the 2A, which is 42 in hex. So that works out. And so, again, you just have to worry about these mismatches, or just make sure you match everything up. So if I have a signed word, I'll just call it hello. I don't know, I'm just making up stuff. What are they using? Signed word, -5. And so, same thing goes. I could move. This is where things get interesting, right? So move this, move that. But now to make this work, I have to move into AX, because signed word is a 16-bit quantity. AX is a 16-bit quantity. Oops, I'll move hello into AX, call the dump regs. This essentially is commented out because we're going to blow it out, but just to show. Here we go. So now this is where the fun of this is this right? FFFB, and everything else is 0. But I used only the 16 bits, so I only used the first and the back half of the entire register. And you can see, what is -5 in binary? But that, right? So because B, C, D, E, F, yep, it is right. That is -5 in binary. Or in hex at least. So that goes with that. And then just finally finishing up with a double word, hello there, and then just a double word, and then just put a 4 in there. And it's the same deal. Now I have to move into the entire EAX register, the word there, that's the variable, and now, I hate when this happens, there we go. And so now there's my 4, because the entire EAX register is taken up by this. And I could prove this by commenting out this guy now, right? Because this sets everything to 0 ahead of time, but this definitely goes ahead and plays with the entire EAX register, so there's no need for that EAX, 0 move right now. Okay, so that basically handles that handles the move instruction. Talk about it before we talk about it here. Okay, so the move instruction, again, is just basically the assembly language version of an equals statement, single equals statement. We copy data from the thing on the right to the thing on the left. So it's pretty much equivalent to what you've done. I mean, I can't imagine it's not equivalent to things you've done in every other programming language you've ever worked with. So just rules to follow. This is the important one here, especially when we get to more complicated tasks. You can't have more than one memory operand. You can't have more than one variable. I cannot just say, one thing here, I cannot just say move. Oh, I don't have anything that matches here. I just call it every. Then put it up as a D word, make it 7, something like that. I cannot move there, comma, every. I cannot move RAM to RAM, variable to variable, because you have to use a register for a move statement. So you get an error in that, and again, that very, very clear, sarcastic, invalid instruction operands. And it's like that one screams out like, what am I doing wrong? They match up. It's a double word, that's a double word. What's wrong with this? And what's wrong with this is you cannot move RAM to RAM. You would have to move RAM to register and then the register to the RAM to make things work. So we'll show this in a few examples. I won't do it right now, but you need 2 separate lines of code to move from variable to variable. Other rules that you don't necessarily care about, you can't move an immediate value into a segment register. You just can't say, oh, the data segment is now over here, or the stack segment is now over there. You just can't do that. And you cannot directly access certain things like the instruction pointer. Your computer could be hacked really easily if someone could just go in and just say, hey, program, you're now over here, somewhere else in RAM or something like that. So we don't directly allow that. You can indirectly change things with jumps and if statements and compares and things like that. But we cannot do that here just by directly saying, hey, program, jump to here, at least not on this processor. Okay, so as we're saying here, there are, just to show the different operation mismatches and things that can go on. If I have a byte, number's 42, and value is a 19 as a word, and so if I take number, which is a byte, and I move it to a byte register, that's perfectly fine. If I take a word and try to move it to a byte register, I will get an assembler error. I put value, which is a word, try to move it into AX, which is a word, that's fine. I take number, which is a byte, and try to move it into a word, not going to happen. I try to move AL to number. AL is an 8-bit register, number is an 8-bit register, perfectly legit. Value is a word, EAX is a double word. No, not allowed. Number is a byte, EAX is a double word, not allowed. So again, it gets, when you're starting out, yes, it takes a while to get used to these kind of ideas, but once you've been doing this, once you practice, it becomes second nature using and making sure that the things line up. And then we actually have ways we can fix this in the future where we can basically say, okay, number, we know you're 8-bit, but why don't you advance yourself and make yourself 16-bit? And I'll show you guys that in future lectures. Okay, so your turn here for the move instruction. So what do all these lines of code do? Which have errors, which do not? So let's take a look here. And some of these follow those silly rules that you're never really going to see in this course, at least. But at least just understand that there's a lot going on here to make sure that everything lines up. So let's see. C is a word. BL is a byte. Not going to happen. 45 move into DS segment registers. That's like one of those crazy rules that you can't do that. Move C, which is a word, into SI, which is 16 bits. That one, word to word, that one will work. AX to C, that one should work too. Word to word. D into EIP, the instruction pointer cannot be directly modified, so that should be not working. Even though it's a double word moving into a double word, that one should not work. D is a double word, move it into ECX, that one should be okay. I can't say, hey, 25, you're A now. You can't turn a hard-coded number into a variable. So that one won't work. And then this one is that last tricky one again. Even though A and B are the same size elements, because it's RAM to RAM, variable to variable, I would have to do this in 2 lines of code. And there you go. Here is the solutions. Exactly that, right? I can do this, I can't do this, I can do this, I can do this, I can't, I can, I can't, I can't. And so this next slide here just shows you how you would go about doing that last one where you're trying to move A, or is it A into B? Because that's what we're showing here. B equals A, move A into B. And so I have to take A, which is a byte, move it into a byte-sized element, register, and then take that register and move it over into B. So it's a two-liner. And that's just because, you know, the way the address buses and all the wires work up, they can't get two pieces of information to and from RAM at the same time. They only have access to one of them. So because of that, I have to take RAM, move it over to something on the CPU, so then in the next clock cycle or the next operation can go and put it back. So that's what we're going with here. So let's see what's next slides. Okay, so I was discussing this is one way I can actually go ahead and turn a smaller data type into a larger one. So this is kind of a static cast, or just a plain old cast, depending on the language that you're coming from. Static cast is the C++ way of doing things. The old C style casting is what Java is all about. So again, this is what happens when I want to take something that's smaller and make it larger. So I have to basically take a byte and move it into a word or a double word, or I have to take a word and move it into a double word. This is not how you contract anything. This is an extension. And you can see from the name of the, as much as that's a crazy name for this thing, it's move zero extension. So both operands must be the same size at the end of the day, right? So that's what the rule is. But this allows us, this is like one of the few operations that allow us to not have to worry about that, because there's no other way to take something smaller and make it bigger other than to do something like this. So the destination operand must be a register, so you have to do this on the CPU apparently. And so all it really does is, again, it's taking your source and just expanding it out. So zero extension means exactly what you think it means. It means that take whatever, and in this new space that I'm setting up for this thing, put zeros in there, because I'm zero extending out, which means that this is an unsigned operation, because I'm not taking into account the sign of the value that's currently stored in the source. Even though this is a 1, it's an unsigned value, that's perfectly allowed. This is a positive value, and I'm keeping it the same exact value because I'm front loading the zeros. So in this case, I could take, I'm not changing any of the variables, but I'm changing a register to get the job done. So it would be two operations again if I wanted to set up and say hello equals number, because I have to do one operation to do the actual expanding, and then I have to in a register, and then I have to do one operation to expand out into or take that expansion and copy it into the other variable. So like this here. So let me just get rid of all this fun stuff and say, okay, I want to do a move zero extension and put it into hello, and I want to put number. And so again, if I tried this just as a normal move, what would happen? I would get a compiler or assembler error, invalid instruction operands. But if I do a zero extension, I can do this now, because I can take number, which is a byte, and extend it and make it larger. And let's just, for the sake of this, let me get rid of the signedness. It doesn't really matter, but let me just get rid of it. So now, oops. And I didn't follow my own rules. So I say, I can't just do this. This is what I get for copy pasting and talking and thinking at the same time. So I have to move this into a register. I don't mind showing you my mistakes, because programmers do this all the time on TV and all that. They make it look like programmers are these godly things, and there are programmers who are gods, but they still make mistakes on simple things like I just made. And I like you to see that we're all human too. So move zero extension into the AX register, something like this. This is what I'm going for here. There we go. I'm not completely brain dead this morning. And then it's a two-step operation if I wanted to now say, okay, take whatever's in the AX register and put it into hello. And then I call dump regs. Here, I can show you up front here. Let me move into the AX register hello, call dump regs, and then do the work here. So I can show you that hello is -5 to start. And there's my FB. So -5 as a byte is FB. And then afterwards, when I extend it out into the word space, I'm sorry, I'm printing hello, I'm sorry, FFFB. Man, I'm having a morning. FFFB, because I'm using the AX register. And so that is correct. And again, all this extra stuff doesn't matter. Only the AX portion matters, and it's correct, FFFB. And then when I go ahead and do all this operation, move this stuff around, you see it becomes 002A. Again, that is 42 in hex. So I have done what I needed to do. I couldn't do this really any other way. I mean, there are other ways, but this is the simplest way to go about taking something that's a byte and extending it out. And the same would go if I just put EAX. I can't, well, this wouldn't work out. Let's see, build, rebuild. Oops, I want to stop debugging, of course. So instruction operands must be the same size because EAX is a double word, hello is a word, and so that's not going to work now. So let's see, so I could say, let's see, hello. I could put there, I can use there instead of all these other things here. And so I can put there into EAX register. I can call dump regs. I can put number in there. Wait, hold on, let me rebuild. Okay, that works. I can take their double word, put it into EAX, and it'll print out 4. And then I can take number, move extension, because it's a byte, and then move it in there, and then move it over. And so, yep, so you see here now, 4 comes out, because as a double word, there is 4. There it is. And then when I actually go to the move extension, the 42 extends out into the entire EAX register, gets copied over to there. I call dump regs, and you can see the entire register is now 42. So that's what the move 0 extension is all about. So here is then the signed version of that, which is move signed extension. So let's see, let's come back to this. Hello, move hello into, hello is a word, move it into the AX register, call dump regs, and let's see, let's just take a look at that and say, okay, there's my FFFB. So let's just go ahead, let me take hello and put it into the entire EAX register, just to show you now. Oops. I'll have to do, okay, for the -5, I'll have to do a move signed extension. Because as itself, it can't do that. We just showed, right? If I just took hello and just did a plain old move into the AX register and call dump regs, and I do a move sign extension, you'll see in 2 lines here that that moving it into the 16-bit gives me FFFB and all this doesn't matter. But once I say, okay, take hello and now extend it into an even larger space, the entire EAX register, it's now tons of Fs and then a B. So it's extended out. It's used a sign extension because it took that -5 and extended it out. If I use the 0 extension and run this again, obviously you could see that's not what I want. It took FFFB, which is a negative number, and by 0 extending instead of sign extending, I made it positive. I actually turned this into a really large number. -5 became 65,530 or something close to that. And so that's not good. So you have to understand if you're dealing with signed numbers versus unsigned, and notice that you don't actually have to put the S in here, right? That's another little thing. Like this is just, the signed and unsigned is just to help the programmer understand what is being stored in that memory location. So I can bring this back to move sign extension, and you can kind of get a feel for what's going on. So again, there's no real difference, so the sign extension just takes the most significant bit of the smaller data and then extends that out. So positive numbers stay positive, negative numbers stay negative, and because the whole point is to expand out into a bigger space, but then keep the magnitude of the number identical moving forward. Here's something you can't do in high-level languages without multiple lines of code, the exchange instruction. I can actually go ahead and swap data. And so without having to do, like 3 lines of code, I can do it in 1 line of code. So I could go, the only thing is, again, that what kind of reduces the positiveness of this operation is that I have to use registers. I cannot just say exchange. This would be really cool if I could just say exchange there and every. Because that would be great, just to swap 2 pieces of RAM, and I go, nope, invalid instructions. So you would think, oh, okay, that's awesome. So it ends up being the exact same stuff. I have to move something from RAM into a register, then exchange, and then maybe exchange this a 3rd time here, right? So I'd have to move every into EAX. Make sure I'm using double words. Yep, I could do an exchange with EAX and there, and then I would And I say, what have I got, right? So I have two statements here. So I've moved this and that and everything else, and then I can exchange EAX with every again. So it ends up being 3 lines of code. And so let's see, let's move into EAX register there, and then let's move into the EAX register every. And so and then we can see that I swapped things. And if I didn't, I screwed up. And let's see what happens. And there you go. There, so let's say there comes up first. I did my swapping. There is 7. Every is 4. So it still took 3 lines of code to do the work. If you know, as long as the stuff's already on the registers, it's a free operation to you. But if stuff is sitting in RAM, you don't get that option. So yes, but I did essentially swap the 2 values sitting in memory. So just to say, okay, so both operands must be the same size, obviously. At least one operand must be a register, as we showed. You can't have 2 RAMs. And you can't, obviously, you can't just say exchange EAX and 4, because that doesn't make any sense, because again, a hard-coded number can't be turned into a variable. So invalid instruction operands comes up there. So let me put that back. Okay, so let's take a look at arrays. Arrays are not something that's as easy as you might anticipate, or even if you're thinking it might be challenging, at least starting out it is a little more challenging than you might anticipate. Even so there's 2 ways we can represent an array access, at least C++. So you can see this is the traditional method array, square bracket 1 equals 4. So I would say, okay, take element 1. Everything is 0 based, remember. Almost every programming language uses 0 based index accessing. So I'd say, okay, change the 2 that's stored in here and put it into a 4. And so at least in C++, I can use this alternative way of writing code and say, take array, which is a pointer, move over 1 element, so add 1 to the element, and dereference it, basically go to that memory address, and then put a 4 in there. So I mean, that's really what's going on under the hood. And we say this is what the syntactic sugar is what they call it, where this kind of removes you away from what the computer is actually doing to get the job done, because it's taking the 4, or it's taking a memory address, shifting it over a little bit to get to the real memory address, because you're offsetting, and then by dereferencing, you're saying, okay, I know I'm staring at a memory address. I know the number I'm looking at is a memory address. Go there and do something with it. That's the whole idea of what dereferencing is. I know whatever number is sitting in front of me is a memory, but so it's not actually a data member. It's not actually like an integer value. It's a pointer to an integer value. So go there. So it's one extra step to get yourself to that memory location so you could do the actual work. And so I wish someone had described it that way to me. At least that's how I visualize it. That's when it clicked for me, was understanding that idea. And so again, the computer does all this for us, trying to figure out exactly which memory address to address, because it takes the initial, wherever array 0 is, whatever memory address that is, and then it takes that, this is just an example, and then for every element, in this case, since these are integers, it's 4 bytes per element. So if I wanted this element, I got to move over 4, 4, 4, 12 bytes. And so it's essentially the index of, or the address of the first, where the array starts, plus the size of the data type times the index value. And so C++, it's seamless. We don't notice things, but we will quickly notice that when it comes to assembly language, we don't have the benefit of knowing the data type. We're going to have to move byte-wise ourselves as opposed to element-wise what C++ does. So we'll see that in a minute here. So accessing the array, say there's ways to do this. This is where you start using the square brackets to start working through this. So if I have an array, I'll just call it A, and I'll just, this time around, just to start going, I'll use bytes, just like they have, 1, 2, 3, 4, 5. And so accessing this, you can do something like this. You can actually say, okay, move into the AL register. Let me just zero out the entire EAX register to start. And I can put my call dump regs in here. And I say, okay, how about I go ahead and I move into the AL portion of the EAX register, A of 0. And you'll see that you can do this. That's how you access an array, A0. So this is perfectly allowed, and this is where, basically the syntax of C came from, is because if I can do it in assembly language, why change it? Because C++ or C is kind of like a step up, just just basically assembly language minus all the extra little steps that go into it. So, and I can go ahead and do that. And then if I call dump regs, I can see there's the 1. Oh, cool, it comes up here automatically now. And so if I wanted to change this, give me element 4, and it'll give me the 5. There it goes. Oops, now I got to drag it over. Anyway, so you can see there's the 5. And again, on a byte-by-byte basis, this is perfectly okay. And what if I wanted to change stuff? Well, how about I move, it's just the other way around. Move into A4, move 62, and then run this again. And now you see, oh my goodness, 3E, right? So that's hex for 62. That worked out perfectly fine. So you can do things this way, or you can do things like this as well, because going back to the previous slide here, this way of doing things now is more like this pointer manipulation method. So you can access, that's why coming from a C++ background, a lot of times this stuff kind of is a little more intuitive than coming from Java or Python. It's just because you've kind of already dealt with that low levelness that you don't necessarily get from these other languages. But I can do this exactly the same because basically I'm doing the same stuff. I'm taking A, which is a pointer, and basically a pointer to the first byte of the array, and then I'm moving 4 bytes over, or 4 elements over. And so it's the same deal here. I still get 3E out of it using the same nomenclature. So and you can do what, and you can combine them. I don't recommend that, but again, they're identical things when it comes to how it works under the hood. And so just to finalize that. Okay, so here's the big one here underlined, that this only worked because we're dealing with bite-sized elements. If we were dealing with word or double word-sized elements, we would have to fix this and change this, and we will see this probably in the next slide or very soon thereafter. And here it is. Here is something, if I just change this into a double word and I try the same stuff out, what do I get? I get a break first off because the operands are not the same size. And so that's a problem, right? Because A plus 4, like A is a double word array now. So A, this doesn't match up because this is expecting to be a double word trying to move into a bite-sized element. So I have to make this thing work. How far does everything break? I don't want to get into too many details just yet about how to make this work for sure, but does this work for us? There we go. You're like, okay, there is, and you're like, what's the problem here, right? Like I moved into A4, I moved to 62, and it works. But the problem is, just from the previous slide here, every increment of that pointer is 1 byte, not 1 element. So what really happened here by doing A4 is I moved over 4 bytes. So instead of going over and thinking I changed the 5, the value of the 5 into 62, what I really did is take this and move over 4 bytes and actually change the 2 into that. And so that's a big problem because I have to think byte-wise. So I have to multiply. So it's like this comes back to this formula too. It only worked for bytes because the size of the data type was 1, and multiplying by 1 worked out. But the address, the true address of where this thing is in memory, has to be size of data type times index value. So let's see. So coming back to this, so signed double word, if I wanted to do this, I have to take that 4 and multiply it by 16 because I need to move over to this element, which is 4, 8, 12, 16 bytes over from the start wherever A is. And of course, you won't see any difference. This is a part of the fun, in quotes, of assembly languages. You don't see the difference. The result is exactly, I can't get up there, I get cut off. But you can't, you would never notice the difference, but under the hood, that array is completely wrong the other way. And this is now correct. And so, because whatever, that 2 would be completely blown out. If I went to go back and try to use it or print out all the bytes of the array, you would see that, nope, this is not correct. And so, across the board, you have to understand that. And so these are just more examples of the same stuff. You have to move over the number, take the number, the element times the size. So like if I want to go and get the first element, the second element of a word-sized array, I got to move over 2 bytes. If I want that for a double word, I got to move over 4. And if I want it for basically a byte array, I just move over 1. So that's why a byte array, if you can get away with it, is the easiest way to go, because it depends on the values you're trying to store, of course. But if you can get away with a byte array, you go with it, because then you don't have to think more than just basically the C way or the Java way, because every element is the same size as the data type. Okay, so let's see. Our turn here. Here we go. So let's see, let's put this together here. So I have an unsigned short array, and I'm trying to swap some values around. So that's what I'm trying to get across here. Let's figure this out. I have, let's say short, so it's a word, and it's unsigned, so something like this. And I'm starting it out with 1, 2, 3. So that is what this is telling me. This is my given. I have a short array, unsigned short array 1, 2, 3, and I want to swap some stuff around and make it 3, 1, 2. So how are we going to do this? I'm going to just pull up the code. I've made a few mistakes today, so I want to make sure I do things the right way. And so what I can do here is what you see here. This is this is one way of doing things, the inefficient way. And so this is something any newbie, including me, would do. And you'd be like, well, why don't I just use 3 registers to set everything up, and then I can just basically, once I have 3 registers with the values stored inside of them, I can just go ahead and then just move them to wherever they need to truly go at the end. So essentially kind of like 3 swap operations, but it's 6 lines of code as opposed to the 9, because if I just swapped and swapped and swapped. So it works, but there is a better way to do this using the exchange operation. And as I showed before, the way we did things with RAM to RAM, it was pretty inefficient because it still took 3 lines of code to get the 2 things to swap. But now we can be a little more efficient because we have more than 2 things that need to swap, so we can kind of take advantage of that and actually do this in 4 lines of code. And so I can say, take whatever is in A plus 0. If you want to think of it that way, just A 0. Or the other way again is to do A plus 0. There's 3 different ways you could do like just A, which is the first element. But just to stay consistent with what you guys probably already know, I could say, okay, let's move that there. And so now the first element, the 1, is now stored in the AX register. And so now what I can do is I can exchange that, because A0, and I could just exchange it with what I need to. And again, this is a word-sized array, so I'm trying to move that 1 into the second element, because that's what I'm trying to finalize here. And to do this, this is where things get tricky. You would think, oh, A1, but it's A2, because this is 2 bytes per element. And so to be able to do this, I got to move over to A2. So far, so good, right? Okay, so then now the 2 is stored in the AX register because I did the exchange. And so I need to put that 2 into the last element. So I can go ahead and do that. And I can go, so there we go. So now I swapped the 2 that's in the AX register with the 3. So the 2 is now, what are we looking at here when this is all said and done? This is still 1, 2, 3 in memory. And so now this has been, let's see. This is now 1, 1, 3 at this point. And just remember, the AX register is holding that value. We didn't lose the 2. And so now at this point, we're looking at 1, 1, 1, 2, with the 3 being stored. And so now the last item of business is just to do a move into, back to A0, whatever's in the AX register. And so you could do an exchange here, but it's, you could imagine exchange is going to be slower than a move, because a move is just taking data and just slamming it and moving it over to a different place. But an exchange involves at least 3 steps, right, to move things from point A to point B. So the move is the smarter way to go about doing this. And so I can't really, can I do this? I don't want to take too much time, but it does work. And if you really want to go ahead and set everything up, you could just move into, move sign extension if you want, or something like that, into the EAX register, whatever's at E0. It actually does that. I'm going too far, because this isn't going to work out like you, oh, maybe it is. Here we go. There's my 3. I guess it does work because this is a word array. It's funny sometimes how certain things work like you expect and sometimes they don't. And so I called, let me copy this over. And so no, it doesn't work So this is the fun of this, right? I screwed up because I used elements and not byte size. So 3 comes out, that's correct. And 100 comes out. Oh my goodness, and that's because all the bytes are in a weird order because of the little endianness order. And then in the last one here, that one's correct because A2 is actually on a word boundary. So in my haste here, this is what I need to do, is say, give me byte 0, give me byte 2, give me byte 4, and you can see that it comes out as 3, 1, 2 like I'm expecting. And now that I have this code, if I do go ahead and put this before as well, you'll see that I do start with, it's hard, here we go. I have 1, 2, 3, and it becomes 3, 1, 2. So I've done my job. I've done what I'm supposed to do for this problem. Okay, one more example of this, and in this case, I'm just going to talk about it. I'm not going to write the code. You have the code in front of you. You can go ahead and transfer over. Some of you even have the PowerPoint, so you could just copy paste the code. But I want to take these 3 bytes. This is, think of this as a byte array, and I want to add the 3 quantities together and get the correct result. And depending on how you look at this, you're going to see there's going to be an overflow. But I want to find a way where I can not have the overflow happen. So let's take a look here. Let's just take a look at the first thing you would try to do. You'd be like, okay, I have my byte array, 80 hex, A5 hex, 66 hex, and then all I'm going to do is move the first byte in to a register and then add the next one, And so because all the bytes are 8 bits large, you're like, okay, good to go. And there's overflow because you could see that this is, this is unsigned stuff. So A plus 6 alone is, pushes over into, into another digit. I need 3 digits to make this work. And so if this was C++, we wouldn't care. Well, we would care about the overflow, but there's nothing we could do about the overflow occurring because unless we went ahead and did sign extensions, static casts, all sorts of things to do this ourselves. We would have to take bytes and extend them into words and then add the words together. And that's kind of what we need to do to solve this problem. Again, if this isn't a problem to you, if the overflow is fine, you're done. But that's the lazy approach. Let's see about doing things the better way here. So you're like, well, how about I just go ahead and I set up AX? Instead of, if AL is the bad way of doing things, why don't I just use AX? And you're like, yeah, you're getting closer to an answer, but then you're going to get a size mismatch. Because taking A as a byte array, an element is a byte, trying to move a byte, which is 8 bits, into a 16-bit spot is not going to work out for us. So this approach, you're getting closer to an answer, but it feels like you're getting further away because you're still going to get weird errors. So what about this kind of solution now? Okay, so let's run this line for line, this approach. So I'm going to take A, which is a byte element, starting from the first location. So I'm taking the 80, and I'm going to move it into the entire AX register because I'm doing a 0 extension. So this takes the 80 hex and puts it in as such. There's my 0, there's my 80. And so don't mind all this extra stuff. It's just the way I can get Excel to kind of visually display this. So, okay, so that is the first line. You're like, okay, now why don't I take whatever's at A plus 1 over here, the A5, move it into the BL register. And so you're like, okay, I'll take A5 and put it over here into BL. And so there we go. And now we're like, well, why don't I add whatever's in the entire BX register and add it over to here. And this is where you can see the problem. And the problem is we don't know what's in the BH register because no part of this code has gone ahead and discussed what's going on. So you can think of this as question mark, because it's completely random whatever's going to be inside of there. And as you can imagine, if you're going to have a random value and you're using it as part of an addition or any operation, whatever you get out of it is going to be basically, who knows, right? Undefined. There's no way to know. So we're still getting closer to a final answer here, but this isn't going to fly. So nothing after this point matters because the result is just going to be complete gibberish inside of here. You'll get the correct value on this end, whatever 80 plus A5 is, but after that, nobody's going to know what's going on. So the final solution is as simple, like there's other ways to do this as well. This is just one of a couple ways you could go about doing this. And now we set the entire BX register to 0 before we start doing everything else, and now it's all going to work. So I can take A, which is 80, 0 extended into here, and there we go. And there, now that's the first step. And then I can say, oh, now I can move A plus 1, which is the A5, into BL. And so, cool, we got that going for us. And now we can add the two together. And so what is 80 hex plus A5 hex? That is 125. I just did the math and just paused it. So 0, 1, 2, 5 is the result. So they say that's what, when I add into the AX register, BX stays exactly the same. And then now you do what you're thinking here. I take whatever's at A plus 2, which is 66, move it into BL, and I do the same operation, and the result I get is 18B. So 0, 1, 8B is the result, and the AX register holds the complete value minus, I would say, with the ability to handle the overflow. So you actually could go ahead and turn 3 bytes into a word that holds the resultant value. And so BX register has been modified, and AX register holds the end result. But at the end of the day, we have the result we're looking for. Perfect. So let's move on to other things. Moving on to other things here. So now, increment and decrement. So this is a very specific add or subtract, obviously, right? Because a lot of computer science, everything, a lot of things computers do is just to add or subtract by 1. So there is a very specific operation that can handle that. So it works exactly like we expect it to. It's an inc, A. So my question when it comes to C++ or Java, is it more like the pre-increment or the post-increment? And in our case, because that whole idea of pre versus post increment is a very high level idea, think of it more like the pre-increment, because it's an immediate increment, because it's the only thing it can do. It's one line of code. It's not like C++ where you can combine a lot of things onto one line of code. It's all you can do in one line of assembly language code. So it is a pre-increment that we're doing. So you just have to watch out, because again, when you're dealing with the parts of the registers and whatnot, you have to just understand that you're only dealing with the register that you're talking about in the current line of code, and nothing else matters. Even if you extend out, and overflow does not, as we just showed in the previous example, overflows don't even go into the next part. Like if I used AL and it overflowed, it doesn't go into AH. It just goes into the carry or overflow flags, that kind of stuff, just to set the fact that something went wrong. And so maybe I can maximize this for now. So take 1000 hex, increment it, 1001 hex. Take 1 million and increment that, 1,000,001 hex. So here, take FF and increment the entire AX register, you get 1011. And just, all that blabbing from a minute ago, what do I do if I have 00FF and I only, as an AX, and I only increment AL? And so the high end, the AH portion of this register is not modified, only the AL is, so you actually end up with 0 out of this thing, because again, you're only tinkering with whatever you're talking about as the destination operand. And so in this case, I moved zeros in there, but then I didn't touch them on the next step. I just dealt with the FF sitting there. And decrement is exactly the same idea. You're just going to have to get used to going from 00 to FF instead of 00 to 01. So take 1000 hex, subtract off, you get 0 FFF. B is now 0 with a ton of F's. Decrement 0, you get -1, which is max int if it was unsigned, FFFF. And again, if I took 0000 and decremented just the high end, notice then again, I'm not touching anything else but just the 1 byte there, the AH portion of the AX register, so it's FF00. So using these two things together real quickly here, using this with an array, so what do I get if I take on a byte by byte basis? Say, get me the first byte and move it into AL. Okay, AL is going to be FF, of course. And so what happens then if I take this plus 1, move it into AH? Well, this is going to be a 0, so I'm going to move 0 into AH. And then what do we do from there? So let's take a look. Here are the answers. So FF goes into this register, 0 goes into that register. I decrement the AH register. Yep, now it's FF. I increment AL. I basically swapped everything here. You know, the -1 and the 0 got swapped in the two spaces. And if I decrement the entire thing now, okay, so think about how what we're dealing with here. This is the entire AX register. When you get to this last line of code, is FF00, high then low. But if I decrement the entirety of the whole thing, then it actually becomes FEFF, because now I'm subtracting off from the AL, but now I do carry and pull from the rest of the AX register because I'm specifically using that entire register. So again, do this a few times, write this out if you need to. But again, it gets a little tricky sometimes because you're dealing with, if you're dealing with byte elements, then using the word elements, because they're all sharing the same memory. So if it clicks, it clicks, but if not, it takes a little effort to understand. It's like a union. The EAX, AX, AH, and AL are all intertwined into the same 32 bits of storage, and you have to know how they work together. Okay, the last few things. Add instruction is like a plus equals. So just think EAX plus equals A, or in this case, that's a move, sorry, that's EAX equals A, then add is EAX plus equals B. So, you would think there might be 3 operands, be like, okay, what is the, because what is a plus equals, right? But it doesn't work that way. So you're going to have to worry to say, this is EAX, this is what's going to be modified, and this is going to be added into it. So, same usage rules as the move operation, but other than that, we're good to go here. So again, I can't just add the two together. I have to move something to a register. So 10,000 hex gets moved onto the register. We add 20,000 hex to it. We can add just to the AX portion, because this is the entire EAX register, 8 hex digits, 32 bits of storage, and say, okay, this would be the same whether I added it to AX or EAX. I get the same result. But if I add 1 to EAX, in this case the entire register, I get 40,000 hex. But then if I add 3, this is where things get a little weird here. If I add 3 to just AH, this is actually correct, because this entire thing is EAX. The low 4 is AX, and of that, these two here this byte here is the AH portion. So I'm actually modifying 0, 0 inside of here and turning it into 0, 3. So again, that takes a little, we don't do these things offhand, but if you understand what's going on, like everything else is going to come a lot easier for you. Okay, sub is the exact same thing. It's just a minus equals, and again, you just have to get used to flowing over into the negatives with everything here. So if I take 10,000 hex, move it in, subtract 2 off, I get FFFE. And then if I subtract off EFFE from that, I get 1, 0, 0, 0, just hex subtraction, which is perfectly fine. And then if I subtracted 1 from that, I get 0 FFF hex. If I subtract 1 from just the high portion, kind of like I just described a second ago here, that just these two digits gets modified, subtracted off, so you get 0 EFF. And then if I take just the low portion and subtract 2, then I can go ahead and FF becomes FD, because FF becomes FE, and then FE becomes FD. And so everything kind of works out there as well. Okay, so the final operation for today is the neg instruction for negate. So obviously this can only apply to signed values sitting in on a register or sitting in RAM. And so it turns any negative number positive, any positive number negative. It's essentially your 2's complement. And it's like almost any negative number turns positive, but every positive number turns negative. So it's one of those thought experiments. What number doesn't this work for? I'm not going to tell you now. I'll probably tell you in another video, but just think it out. Which number would not work? So just to say, just negate, right? So if I move A, which is -1, which is FF, and put it into AL, the AL register will hold the -1. If I negate FF, do the 2's complement. Flip all the bits and add 1. FF becomes 0, 0, and 0, 0 plus 1 becomes 0, 1. So -1 becomes +1. Fair enough, right? So let's not worry so much about this. They'll just go with it and just say if I take positive 32,767 and I negate that, I get negative 32,767. And if I take C, which is negative 32,768, and I negate that, well, I should get whatever the negative of that is. And so for a few more examples here, So just getting used to using arrays with this too. And also the whole thought of what is negation actually doing? Because you would think it's 2's complement. We've shown in previous videos you could just do a not operation and then increment. So you could break it down if you wanted to do this. If you didn't have negate on your CPU, you could, and you had not and increment, you could just go ahead because you're flipping all the bits and you're adding 1. You're always doing that to get the negation of whatever is sitting in front of you. But what really is happening with a negation is a subtraction with 0 and the operand. It's weird, right? But this actually sets up all the flags correctly. So, because again, the flags are what matter a lot of times to determine, do I have a positive number? Do I have a negative value? What happened while the operation occurred? So under the hood, a negation operation turns into a subtraction, but it's non-destructive, meaning it doesn't destroy the operand. So if I did a subtraction instead, it would just completely trash whatever is staring at me. But the negation changes everything, but also affects the flags. Okay, so what are we dealing with? Negate A, and this is weird, right? Because I don't have to use the square brackets a lot of these times, but this is just saying take this 1 and negate it. And in this case, the carry flag gets set and the overflow flag doesn't. And again, you're never going to have to necessarily worry about that. But but the carry flag for everything that isn't 0 will set the carry flag because of the way subtraction works. 0 minus anything will basically flip the carry flag because I'm going from a positive number into a negative one. So here, a plus 1 is a 0. I negate 0, I get 0. Nothing has occurred. There's no carry, there's no overflow because there was nothing to worry about. And now again, if I do the same for a signed byte, negative 128, I negate that. The carry flag and the overflow flag get set, but why is that? Not a question for me to answer today. So putting this all together here, last few examples. My goodness, we're almost done with this video. So let's see something like this. I have an x value, a y, a z, and an r, and here is the formula I want to get across. 26, 30, 40, you name it. Let's translate that, and let's see something like this. So this is how I would go ahead and do something like this. And so I think this is the naive approach. There's a way to get this a little quicker, but we'll see this in a second here. So set up our variables. X, Y, Z, R, they're all double words. R is not initialized up front, and it'll get the result at the end. If you wanted to put a 0 in there, I guess you could, but it doesn't matter necessarily. So there we go with that. And so what am I doing here? I'm taking X. I wish I should have brought this over. But anyway, I'm taking X and I'm moving it into a register. And now I can do all the hard work on the register. And because so in the process, remember when we write code, when this X, Y, and Z are not going to be modified by this line of code. And if they were modified, you would be very angry because what is the compiler doing? Why is it changing all my variables around? Only R is going to be modified. That's the L value of this thing. So that's where using registers is very key here, because the register is a temporary holding zone and it's not modifying anything else along the way. So X gets moved in, I negate it, so I get my negative X, and then all I have to do is add Y and subtract Z. So, and this is a naive approach. Take Y, move it into EBX, subtract Z off, because I'm using the parentheses, right? And then so now the quantity Y minus Z is stored in EBX, and then I can add the two together, because it's this quantity plus this quantity added together to get the result, and then move whatever's in EAX over to R. And so I said it's complicated. It's 6 lines of code. But we can simplify this if we use a little bit of algebra. And so you'll see for those of you in class doing homework assignments, do some algebra up front and simplify your process. You don't want to be writing 50, 60 lines of code when it all breaks down to 5 or 6. Like the compiler doesn't care, the assembler doesn't care. But you as a human being, you're going to make a mistake if you turn something huge, and if you don't turn something huge and you can reduce it down algebraically. So here we go. I can take this problem and I can work it down. I can just algebraically manipulate everything around and just move the negative X over to here, and you can see how things get simplified. Move Y into EAX, subtract Z, subtract X, move it to R. 6 lines or 4, a lot simpler code because we're humans, and when it comes to this kind of thought process, for now, we are better than computers. So the same kind of idea here. have x, y, and z in an R, so x minus quantity minus y plus z. So let's just get right to it and just kind of reduce this, because this I can slam the negative through here. So this is the equivalent to x plus y minus z. And so we won't even worry about this, but you can see this becomes x plus y minus z with a little bit of algebraic manipulation. And so it's a lot simpler than this approach with negations and adding and doing all sorts of stuff. It's 4 lines of code here. 2 of them are just the moves. So put x onto a register, add the y, subtract the z, and move it over to finish the deal. And so again, the homework assignment is just getting you used to variables and just getting you used to the simplicity and just getting you used to just getting these things going and showing the end result. Of course, you could call dump regs on this to see that EAX register holds the value that you're expecting, because what is the end value but 1 plus, it should be 0, right? 1 plus 2 minus 3, R should hold 0 at the end of the day. All right, so that covers this video. So just getting you started. So I say this is basically a big jump here, because we're jumping right, literally jumping right into assembly language now, and more things to do. This is just getting addition and subtraction working, and now we have to do if statements and loops and all sorts of other things. So this is the time. Get your questions in. swardb@cud.edu. Comment here on YouTube. You get the picture. It's a great place to get a hold of me for anything. And I guess we're ready to move on to the next video. Thanks, everybody. See you next time.